Welcome, EBS viewers. My name is Professor Brian Schmidt of the Australian National University. And as part of the episode of Great Minds today, I want to talk about my own personal journey in helping discover the accelerating universe. Now, in an expanding universe, as we have learned, there can be a variety of outcomes. As the universe expands, it can keep going on, not slowing down at all, and go on forever. This infinite universe has a very different future than a heavy universe, a universe whose gravity slows things down and eventually stops the expansion of the universe and puts it in reverse. Of course, there's the just right universe, the universe that comes to rest at an infinite time in the future. This just right universe is also just right because people who try to understand the very earliest times of our universe and think that the universe may have been created in something tiny, infinitesimally small, and expanded beyond any amount that you could possibly imagine in a period known as inflation, predict that the universe might be just right. Now, in 1994, I was just finished my PhD measuring how fast the universe was expanding now, and I pitched to Mount Stromlo Observatory here in Australia a project where I could look into the universe's past by looking very, very far away and seeing how the universe's expansion changed over time. If the universe in the distant past was expanding at the same rate as the present, then I know that the universe is not slowing down, that the universe is very, very light and will continue to expand forever. On the other hand, there's this critical trajectory, a line in the past where if the universe is slowing down faster than this rate, I know that the universe is heavy enough that the universe will stop expanding and be finite in the future. It will come crashing onto itself in the Gnab Gib. So that was my pitch. And the reason I could make that pitch is because in 1994, I was born at just the right time to go through and do this experiment. A group that I was working with as part of my thesis in Chile had discovered that type 1a supernovae, exploding stars, could be used to measure distances very accurately. So what's a type 1a supernova? It's a beautiful object that is 5 billion times brighter than our sun, and it is the end of the life of a star, or actually a binary system of stars, where a white dwarf and another star, maybe a white dwarf or maybe a puffed up red giant, a red giant star we think is the end state of a star like our sun. And in this binary system, there will come a time where one star will be able to donate its material to the other star. For white dwarf stars, it might be because they actually merged and happens very quickly. Or it might be for a binary system with a red giant star, that the red giant star, as it starts to use its hydrogen in its core, puffs up, and as it puffs up, it can donate material to the white dwarf star that's next to it. White dwarf stars are the end state of a star like our sun, and so in a binary system, it's quite a complex dance that these stars do over time, with one star first donating material to the other star, and then the other star able to donate it back. We're continuing to understand how this dance actually occurs in nature. But we know that at a very particular time, that if you donate a particular amount of material, such that a white dwarf reaches 1.38 times the mass of our sun, a number calculated by Chandrasekhar back a long time ago now, that gravity overcomes the ability of the star to push out against gravity, and the whole thing wants to start to collapse. But instead, the carbon and oxygen that this star is made out of is essentially a thermonuclear tinderbox, and the whole thing ignites as a giant thermonuclear bomb. It takes the carbon and oxygen and moves it into nickel and iron and releases a huge amount of energy, as I said, 5 billion times more than what our sun shines with. And one of these objects, as it rises from nothingness to this incredible brightness over 20 days, ends up often outshining the entire galaxies of stars that it's made of. After they reach their peak brightness, powered by the radioactivity and all the material made, they slowly fade away into nothingness over time. Now, we can see remnants of these stars in our own galaxy, but they're very rare. They only occur every several hundred years. Tycho Brahe, which we talked about earlier, one of the great measurers of the planets, actually observed in 1572 one of these objects, known as Tycho's remnant now, and we can see a ball of iron and silicon and oxygen expanding at a good fraction of the speed of light, even to this day. These are where the iron that makes up the Australian continent and is so valuable to Australia's economy, that is where most of this iron was formed. The reason I like these is because they are so useful for measuring distances, as figured out by my colleagues in Chile. They realized by measuring how fast these objects rise and fall, you could calibrate how many watts they were as light bulbs. And that enabled us to measure distances with them to better than 5%. And because they're so bright, we can see them all the way across the universe to roughly 10 or even 11 billion years into the universe's past. Now, the other thing that happened in 1994 was we developed the next generation of giant telescopes, the 8-meter class telescopes, the first of which was Keck in Hawaii. The other development that occurred at this time were large digital cameras. We're being filmed right now with the successors of these digital devices that were sort of brought from the military into civilian life by astronomers. And in 1994, the first big format, 4K, so quite small by even what we have in our phones today, was developed. But these were 100 times more sensitive than the film that we were used to using, and of a scale that when we put them on a big telescope, we could go through and discover for the first time the very rare Type 1a supernovae back 5 or even 10 billion years into the universe's past. So it was a great time to come to Australia and do this project. And so in 1994, just before I moved to Australia, I worked with Nick Sunseth of Saratoloa Inter-American Observatory to create a team of astronomers around the world who had specific skills where we could go through and do all of the steps to make this experiment of looking back into the universe's past. Now, we weren't the only group doing this. There was another group competing with us out of Berkeley, led by Saul Perlmutter. And we had a lot of competition between the two teams. And the competition was good because we always knew there was someone checking our work. But we could also learn from each other's ideas and from our mistakes. And so a competition to go through and unlock the universe's past started in 1994 and culminated in 1998 with a discovery that I'll tell you about in just a second. But I want you to think what we had to do. This was really hard. It was a time when computers were slow and we were just getting used to digital images. We had to go through and sift through roughly 50 gigabytes worth of data in a night. Doesn't sound like that much now, but the computers were 1,000 times slower than they are now. And hard drive storage that we're quite used to now, or quite frankly, we use all sorts of other things. We don't even think too much about hard drives. We're tiny. A 10 megabyte drive was quite common, and we were just seeing, for example, the first large format drives. And so we had to go through and link together all of the computer equipment at an observatory to make it able to go through and process the data quickly. And to process the data, I had to write lots of software to align images, to subtract the images after making them look almost identical, and then looking for a needle in a haystack. And when we did this, and I can tell you my software was not perfect, many of us had to sit and sift through the mistakes that the software made and find an object, for example, an object that we found in 1995 when we were able to go through and figure out how far away it is. It turned out it was 5 billion years in the universe's past. It exploded before the Earth was formed. And we had to do all these discoveries very quickly because we needed to go through and take spectra. Spectra is where we spread the colors into the rainbows, and the big telescope, the Keck telescope, was really required to do this well. We could just barely do it with the existing telescopes pre-1994. The Keck telescope made it much easier. But we had to do it within a few days of discovery, or else the objects would fade into oblivion and we wouldn't have enough light to go through and get their redshift and confirm that this actually was a type 1a supernovae and not some interloper of, for example, a flare star in our own galaxy or something whose distance would not be of use to us. And so this was a very hard set of work that we all worked on. And after doing it for roughly 3.5 years, we were able to, the very end of 1997, go through and make our first major diagram where we could compare the past to the present. And in our team, we had a young astronomer, Adam Rees, who I had worked with as a graduate student, who was in charge of writing up the data this first time. And I remember in 1997, Adam sending me a figure that plotted the objects from about 5 billion years in the past to the present objects that the Cerro Tololo team had done in Chile in the years before. And what I saw surprised me, because the distant objects were not in the part of the diagram I was expecting. They were not in a place where the universe was slowing down by gravity. Rather, they were above the line. They were in a position of the diagram where the universe was expanding slower in the past and had actually sped up over time. Now, when I saw this, I first assumed we had made a mistake, but we checked our work, the entire team. But by the early 1998, we had realized we could not make this result go away. And so we announced to the world in February 1998 that we had evidence that the universe was speeding up over time. A crazy result that I could not believe to be true. But it was revealed that Saul Perlmutter's team had come up with the exact same independent discovery that we had, and were also trying to understand how it could possibly be true. So in 1998, these two teams announced the discovery of an accelerating universe, and that is something that we collectively were given the Nobel Prize for in 2011. But why would the universe be accelerating? Well, that is what we're going to talk about in our next installment of this Great Minds series.